quantum optics and quantum information, cold collisions, Fano and Feshbach spectroscopy, condensed matter physics, superfluidity, superconductivity with cold atoms, orbital angular momentum of light, etc., etc. With that introduction, I would like to invite you to share your slides and for the talk. So the title of his talk is Ion Atom Hybrid Quantum Computing Platform. Professor Deb?
Yeah. Thank you, Chairperson. Let me give a minute to set my file. Okay. Here screen. Can you see my screen?
Yes, we can.
Okay. Good. Screen mode. Okay. Very good. Okay. Thank you very much for the kind introduction. I can't see my screen properly. Just okay. So
we can see your screen.
Yeah. So the title of my talk is Atom-Ion Hybrid Quantum Systems. So before I start my talk, let me first thank the organizers, particularly Prashant, for inviting me and for giving me this opportunity to present our work. So this work has been done with my co-workers, Shubhra Mudli, Shubhanko Mal, and Anushree Deb. Shubhanko has just got his PhD from Kolkata University last month, and Shubhra is a second-year PhD student, and Anushree is a third-year PhD student. So this is based on our recent work, ion-mediated quantum correlations between two distant atoms. So this work is ongoing work. It is to be submitted soon. So the purpose of my talk is the following: to show that it is possible to generate a ion-mediated interaction and quantum entanglement or quantum correlations between two Rydberg atoms trapped in optical tweezers, which are separated by a long distance of the order of 10 micron. So you know that Rydberg atoms has very unusual properties. They have very long lifetime and very long coherence time. So we are considering a hybrid system where a single atom will be trapped inside a Paul trap and will integrate Rydberg atoms with this. So let me move on to the next slide. Okay, so the plan is the following. First, I discuss as introduction a little bit about quantum computing and quantum simulation and various platforms for quantum information processing. Then I would discuss atom-ion hybrid systems, why hybrid systems are important, and atom-ion hybrid system is a new system which has some prospects for doing quantum information processing. And then I will discuss in detail our model, ion-mediated quantum correlation, and phononic coupling between two distant atoms, then results, then discussions and conclusions. Okay, so as introduction, We know that entanglement is a resource for quantum information processing and quantum communications. So in this conference, many speakers have spoken about this entanglement and quantum information and quantum computing as well as quantum technology. So as the title suggests, it is quantum information and quantum technology. So it is basically to manipulate the superposition states of qubit and their entanglement that leads to what is called quantum gates. And when one integrates many gates and do information processing, what is called quantum information, then we have quantum computing and quantum. But not only for quantum computing, the applied quantum mechanics is about also many other tasks like quantum simulation of quantum many-body systems or any quantum systems which is hard to solve. Then we can simulate using a quantum computer. And then also we can do teleportation. And another important area is quantum sensing and metrology using quantum mechanical principles to make new devices. And of course, there is quantum computation. So all these aspects of new quantum mechanics or the new revolution of quantum leads to what is called quantum technology. So on the fundamental science front, it is a new way to treat many-body physics from quantum information theoretic point of view. So not only quantum physics, but quantum chemistry is also enriched with this new development. So then one may ask the question, what is the role of quantum entanglement in quantum chemistry, particularly in, say, quantum in chemical reaction dynamics and so on. So we can think of various platforms for quantum information processing, such as, so before we talk about various quantum platforms for interesting quantum tasks, so let me remind us about these 5 criteria of Di which are very well known. So in order to make a quantum computer, we have to fulfill 5 basic criteria, which are the following. So we should have well-defined qubits and that are scalable. Then we have to initialize the quantum states, okay? And in a unique, so you have to prepare the quantum system in a unique pure state to begin with. And these qubits should have long coherence times, not only single qubit. If we have multiple qubits, then they should have long coherence times. And one should have universal set of quantum gates, which are single and 2 qubit gates, and single qubits and quantum and CNOT gate. They will form a universal class of quantum gates, which can be used to do quantum information processing. And then we need to have qubit specific measurements, which will lead to the output and as readout output. So about various quantum platforms for doing quantum information processing, one important platform is superconducting circuit QIQT for quantum computing. And this system is very interesting because it satisfies all these 5 criteria. Even one can scale the superconducting. And then another important quantum computing platform is ion trap quantum computing platform. But ion trap is also used to simulate quantum many-body systems and spin systems. But then in ion trap, scalability is a question mark because ions interact through long-range Coulomb interactions. And if you want to scale it to many qubits, then there is a problem because the number of modes becomes quite large, and they talk to each other. And then, so that is an issue in ion trap quantum computing. Then another important platform is the neutral atoms in optical lattices. But then neutral atoms, if you prepare them in the ground states, then between two lattice sides, the interaction between the atoms is almost nil, because the neutral atoms in ground states, they interact basically through short-range interactions. The van der Waals interactions range is also very small. So in the optical lattice, the lattice spacing is typically of the order of half a micron. And in that, then it's so if you want to make a 2-qubit gate, then you need some sort of interaction or correlation between two atoms. So so people are thinking about the Rydberg atoms, because Rydberg atoms interact quite strongly. I will go to this aspect of Rydberg atoms. So in neutral atoms, the criteria 4 and 5 are still issues, that universal set of quantum gates, if we consider neutral atoms in the ground states. Then other platforms are solid state spin systems and photonic systems. Then we know this nitrogen vacancy center, quantum dots. So these are among the solid state systems. Then one may think of as quantum platform neutral atoms in the designer lattice, so optical tweezers. So which is the object of today's talk. So this is a way out to fulfill the other criteria, because in the optical tweezers, then you can design the system as you wish, because it is a bottom-up approach that one can make arrays of optical tweezers. And if you can trap Rydberg atoms in the optical tweezers, and then at long range, long separation between the atoms, you may have strong interactions and correlations between the neutral atoms. And Rydberg mediated interaction is very important in the neutral atom quantum platform. And then we have this ion atom. So this is today's discussion. The subject of today's discussion is ion atom hybrid system. But in the ion atom hybrid system, this quantum gate operation is yet to be demonstrated. So, but it has new prospects for making an interesting system for quantum computing and quantum and other tasks. Okay, so ion atom hybrid system. So hybrid quantum systems are useful for performing multitask in various areas. For example, quantum computing and quantum simulation, quantum communication, quantum sensing, quantum metrology, quantum materials. In fact, these 4 areas, what are called 4 verticals or 4 thematic hubs, as the government of India recently announced this National Quantum Mission. So these 4 areas almost cover the entire gamut of quantum science and technology. So among the hybrid system, one can say that this superconducting circuit QED is a hybrid system, because then one can integrate a superconducting disruption circuit and microwave cavity QED. So microwave photons, unlike optical photons, one can control and one can make a good cavity, very high quality factor. And this Josephson circuit, it's a LC circuit without any resistance or without any loss. And when one quantizes this circuit, then one gets enharmonic ladder of states, oscillator states or harmonic oscillator states, and one can controllably choose any two levels as qubit in superconducting circuit. And then one can couple these superconducting qubits, or what are called also artificial atoms, to microwave cavities. And one can then make an array of microwave cavities and Josephson junctions, which then leads to an artificial lattice kind of system. And then one can explore the quantum many-body quantum physics, not only equilibrium, but also non-equilibrium quantum physics. So you can see that this hybrid system offers a lot of opportunities to study quantum physics. And not only quantum computing simulation, but so also perhaps for quantum sensing and metrology, because one can use superconducting circuit system to generate even single photons. So entangled photons people have not yet demonstrated. So, and then one can think of another hybrid system, ion trap and cavity QED, or atomic systems plus photonic systems. So these are important for making quantum network or distributed quantum computing, because the photons carry information, and these are mobile qubits. Photons are, one can use two states, two polarization states of the photons as qubit, and then ions or atoms, one can choose two-level ions or two-level atoms, and then one can do processing at a location or at a station, and send the output or the outcome of the quantum processing through photons at a long distance to other stations or other nodes, and that's how one can make a quantum network. So you can see that the hybrid systems are quite interesting. And so here we will discuss a new kind of hybrid system, which is atom-ion hybrid system. So this practical utility of this hybrid system for quantum information processing is yet to be demonstrated. But in other hybrid systems like superconducting circuit QED or ion trap plus cavity QED, only recently, just last month, there is a PRL paper on ion trap plus cavity QED. One can trap a pair of atoms in a Paul trap, and then inside a cavity, and the cavity photons can be used to send information at several kilometers away, and use repeaters to, so that quantum repeaters to do distributed quantum information processing or quantum networking. So that this has been experimentally demonstrated very recently. So, and recent advances in quantum computing using Rydberg atoms in highly controllable optical tweezer arrays open up new prospect for potential ion atom hybrid quantum computing platform. So original motivation for developing ion atom hybrid traps was to understand low energy ion atom collisions and to explore sympathetic pooling. So many experimentalists have extensively worked over the last 2 decades. In India, Sadiq has done a lot of work on ion atom hybrid traps and ion atom cold collisions and sympathetic pooling. So I refer for a review on ion atom cold collision, this Reviews of Modern Physics 2019, written by Tomja and others. So ion-atom interaction at long range is basically due to coupling of an induced dipole. So induced dipole is atom. You know that ion creates a field, ionic field, and electric field, and this field will then polarize the atom with a charged particle, and so the interaction potential at long range goes as C4. This negative means it is an attractive interaction potential. C4 is a positive quantity coefficient, C4 by R to the power 4. So one can easily understand the origin of this interaction, because if one considers this induced dipole moment, so it is basically the average interaction between the induced dipole moment and the electric field generated by the ion at the position of the electron. And then since induced dipole moment is proportional to this polarizability, this is alpha E, so then you get alpha E square, but E goes as 1 by R square electric field, so you get 1 by R square, R to the power 4 potential. And this C4 alpha Q square by 2 is the long range coefficient. So one can see that ion atom force has intermediate range, longer than the atom-atom force, but shorter than the ion-ion forces, because ion-ion force is Coulomb force, and so it is the longest range interaction. Just one moment. Okay. Okay, here. So developing a ion-atom hybrid quantum system is very important, and because one can then combine the best features of ion trap and or ionic and atomic qubits, because these ion qubits have long coherence time. Coherence time can be of the order of seconds to minutes. And then atomic qubits, they have also long coherence time. But as we know that scalability is an issue in the case of ion trap. So why don't the question is, why don't we then combine ion trap and atomic ionic and atomic qubits, and whether we can utilize all the best features of the two systems. So pulling both ions and atoms in hybrid trap for quantum information processing is a difficult task, but one can think of an alternative. The alternative is to use different traps with control over their relative separation. So we can think of this kind of traps or this kind of systems now because of the recent developments in optical tweezer technology. So now we move to our model. So in our model, we'll discuss ion-mediated quantum correlation and phononic coupling between two distant atoms. So when we tell distant atom, distant means they of the order of 10 micron or even more. So how do we then combine ion trap and atom traps? So this is a pictorial depiction of a pole trap. So this figure is taken from Wineland's Lassus's lecture note given in 2007. So it is published by Elsevier in 2004. So you know that ion cannot be trapped just by static forces. You need also dynamic forces. So one uses this voltage, the time-dependent voltage on these electrodes, the black, and some static voltages also. So there are these are 2 electrodes, and there are 3 electrodes actually. So similar voltage applied this gray electrodes and in between. Then one can form a kind of binding potential or potential well at the trap center, depending on the geometry and the applied voltages. So, so this way in the Paul trap, one can make a trap one-dimensional or quasi-one-dimensional. Even also quasi-two-dimensional is possible. So this is the side view of a trap. So along this is the z-axis along. So then one then if you trap many ions, then they can form a string because of the interplay between the trapping potential and this long-range repulsive Coulomb interaction between the ions. Then they are almost are at a separation, equidistant separation, and forming a one-dimensional array. If the trapping frequencies in the radial directions are quite large compared to the axial direction. So typically in ion trap, the trapping frequencies of the order of megahertz, 1 megahertz. So in our model, then we consider not many ions, but a single ion in a Paul trap. So it is possible to have a single ion in the potential minimum, and one can cool the single ion also in the trap. And then we consider a pair of Rydberg atoms. Okay? So this is a pictorial depiction of our model, that we have an ion trap at the trap center of the Paul trap. And then with optical tweezer, we transport 2 atoms along the z-axis. So this is the geometry. So this is a optical tweezer, and optical tweezer can trap even a single atom. So mostly in optical tweezer, single atoms are captured in the tweezer potential. So what we think as our model, that we don't merge the 2 traps. We control the separation between the ion through optical tweezer. So this separation is more than a few micron. So they don't collide ion atom. We don't want direct collisions. And this distance between ion and atom is much, much greater than 1 micron. And typically, if we consider, say, calcium plus ion and rubidium-87 atom in the optical tweezer, then ion trap size is of the order of 30 nanometer. And this atom trap size, which is the optical tweezer, this is of the order of 300 nanometer. So one can see that there is a clear separation of length scale and also time scales in atom trap. And so this will help us to formulate our model as we discuss here. So in case of ion traps, one can consider 2 kinds of qubits. So hyperpoint qubit, then these are in the electronic ground states, and one can choose 2 different hyperpoint states in the ground state manifold. And by Raman pulses, one can, by largely detuning the 2 Raman pulses from an excited state, one can populate these 2 states and form a quantum superposition of the 2 states under 2-photon resonance condition. So one can then manipulate this hyperpoint qubit with optical forces or lasers. Okay? And there is another ion qubit, which uses quadruple transition, say S and D. And so then this is so one good thing about these ion trap, that they have a long coherence time, so second or minute order. And in case of atoms, then we consider the ground state as state with principal quantum number n equal to 1. And this Rydberg state is accessed or coupled through two photon transitions. It becomes a cascade system. One can use one laser here and another laser here. So then this ground state will be coupled to the Rydberg state. And this can be done by EIT process by fulfilling the EIT conditions. Just one moment. So this is possible because Rydberg state, this NS, and N is much larger than 20. But one can consider not S state, but other states, say P states, but for our model that will be problematic. So we consider only S state. And so this is a Rydberg state. So Rydberg state has also long lifetime of the order of millisecond. So one can then easily couple this S state and this Rydberg state, the ground state and Rydberg state, through two photon transition under EIT conditions. And then the qubit is formed between this ground state and Rydberg state. And then one can then use the long range interactions between the Rydberg atom and the ion to make gate operations or to generate entanglement between atom and ion. But typically this atom, if both atoms are in the S states, then they are spherical symmetry. Then it is the atom-atom potential then goes as 1 by r to the power 6, where r is the separation between the two atoms. So this is because these atoms are spherical symmetric. So this is second order in dipole-dipole interaction. So you get this kind of. So, but for Rydberg atoms, this C6 is huge because it goes as n to the power 11. So if your n is 20, you can see that this interaction potential will be increased by several orders of magnitude, millions order of magnitude compared to the two ground state atoms. But what about this atom-ion interaction? If atom is in the S state, ground state, and ion. So, but ion interacts through its Coulomb force or Coulomb field. So this interaction between atom ion is, as we discussed earlier, that a charged particle and a neutral, the interaction is minus C4 by r to the power 4. But this, if this atom is a Rydberg atom, then C4 goes as n to the power 7. So this atom-ion interaction is also huge. So it is also, so, and if n you take 20, then it will be 20 to the power 7 fold to with that ground state and ion atom interaction. So then what we find that this if ground interaction between two neutral atoms and Rydberg interaction at a separation of say few micron, then this is negligible. There is no interaction. Even in the typical optical lattice, the separation between the two sides is half a micron. So then also this, if you trap only the ground state atoms, then it is negligible. But it is finite and quite significant at a long separation. And between Rydberg atom and Rydberg atom and ground state, it is also quite large compared to ion and ground state. So this is the one interesting aspect of these forces or potentials. That these are atomic state dependent interaction potentials. Of course, they will not depend on ionic state, but they will depend on C6 or C4 is a property of is dependent on the atomic polarizability. So one can then generate this atomic state dependent interaction potential, which is quite useful for information processing. Okay. So as we discussed earlier, the typical harmonic traffic frequency of ion is 1 megahertz, and atom in optical tweezer is of the order of kilohertz. So there is 3 orders of magnitude difference between the time period of oscillations of an ion in the ion trap and of an atom in an optical tweezer. So there is a clear separation of time scales between the motions of atoms and ions. So we can consider this atomic degrees of freedom, their positions and momentum variables. They are much slower than the ionic degrees of freedom. So we can then safely use Born-Oppenheimer approximation to calculate, say, ion-mediated atom-atom interaction potential. So these are called Born-Oppenheimer potentials. So in the leading order, then ion-mediated interaction potential goes as 1 by R⁴, as we have already discussed. So direct atom-atom potential is C6 by R⁶. And so if the atom is in the ground state, then it is negligible. If both atoms are in the Rydberg states, so this is finite, and at a particular separation, a critical separation, these two interaction forces will be of same orders. But at long separation, then this atom-atom potential will dominate. Okay, so one can easily calculate at what distance this ion-mediated potential will dominate between the two atoms, and where this direct atom-atom potential. So this comes out to typically for, say, calcium ion, we have calculated this is 0.5 micron. So 0.5 micron is typically the what is called Rydberg blockade. So in this up to 0.5 micron or of the order 1 micron, this this direct atom-atom interaction potential will dominate below 0.5 micron. But if you go beyond this 0.5 micron separation, then this ion-mediated potential will dominate. So we are considering that two atoms are at long separation, so that we can address individual atoms by using lasers. So then, and we can couple the two atoms or correlate the two atoms at a separation of, say, of the order of 5 micron, 10 micron, using this ion-mediated interaction. So we specifically consider that the centers of the two optical tweezers are separated by more than 5 micron for our calculations. And so in So in our scheme, this ion-mediated atom-atom interaction has essential role. So to understand the order of magnitude of this ion-mediated interaction and quantum entanglement between the motional states of Rydberg atoms, so we consider atoms in the Rydberg state and ion in one electron state. But we can consider this qubit ground state atom and Rydberg state a qubit. But to start with, to understand the order of magnitude, we are not considering here the two internal states of the atoms or ion. We are considering the one internal electronic state of atom and ion, just to understand the phononic coupling or the motional states of the atoms. So the Hamiltonian is this atomic Hamiltonian, and we have this ion atom Hamiltonian. So this atomic Hamiltonian is two atoms. We are considered two atoms, atom 1 and 2. So this is kinetic part. Then we have this individual trap potential, and then we have this PT stands for Paul trap. So Paul trap has electrodes which generate electric fields. So when you place a Rydberg atoms in an electric field, the Rydberg state will experience Stark shift, okay? Because Rydberg states are very sensitive to the any small electric field. So we need to consider this trap-induced this Stark shift. So this will generate a one-body potential also. And then we have this isotropic atom-atom interaction. This is basically van der Waals interactions, the C6 1 minus C6 by R to the power 6. And then we have this ion-atom interaction part, which is ionic kinetic energy. Then we have this trap. So we are considering a cylindrically symmetric trap. And so this we consider this radial trapping frequency omega IR of the ion trap is much greater than the axial trapping frequency omega IZ, so that we can use the approximation, quasi-1D approximation. And then we have this ion atom interactions for the two atoms, C4 by R to the power 4. And then we may have other kind of atom-ion interactions due to, but that we can neglect this for the time being. And so when we solve this Hamiltonian time-independent Schrodinger equation, then we get what is called Born-Oppenheimer approximations. Because we are considering this atomic degrees of freedom, which are this Rj, R1 and R2. So these are very slow variables compared to the ionic degrees of freedom. So while considering the ionic motion, we consider that atomic motion is frozen, because the time period, there is 3 orders of magnitude different between the time periods of oscillation. So we solved this numerically, and we obtained then Born-Oppenheimer potentials. So these Born-Oppenheimer potentials are between the two atoms. And then we solve the atomic part using these Born-Oppenheimer potentials. So Born-Oppenheimer approximation means that atomic wave function and ionic wave functions, they are separable. So there is no entanglement between ionic part and the atomic part. But since we are considering two atom states, these two atoms can be entangled. And we also consider the atomic trap potentials. And for simplicity, we also consider the atomic trap potential is a quasi one-dimensional potential. and it has also cylindrical symmetry. And this axis of atom trap, basically the propagation direction, the mean propagation direction of the optical tweezers, and the axial direction of the ion trap, they coincide. Okay, so we are considering this. So this is actually the atom, two atom and the three body wave functions, which is atom. But if we don't consider this summation over mu stands for all possible quantum numbers, then this is atomic wave function phi mu, and this is ionic wave functions, which parametrically depend on these atomic position variables under Born-Oppenheimer approximation. And if we consider these are two separable, there is no summation, then this is the Born-Oppenheimer approximation. So it means that the ionic and atomic states are separable. But as I discussed, that these two atoms may be entangled. So we resort to an effective 1D model calculation, considering that that in the radial directions, both ion and atoms are tightly conformed. Further, we consider that the atoms are far apart, such that the effective atom-atom potential is smaller than the harmonic oscillator level spacing. So this allows us to carry out perturbative calculations. So we expand then two atom state in terms of harmonic oscillator product basis. So this radial part along these are we consider that atomic motion and ionic motions are cooled, and they occupy the radial ground states, and the interaction potential is not strong enough to excite radial modes. So we are considering only the axial modes, and these are harmonic 1D harmonic quantum numbers, that n and m. And so this 1 stands for atom 1, 2 for atom 2, and we are considering this. So there should be some coefficient C. So this is an error. So these are, we are considering this unperturbed product basis, and there is superposition. So superposition will depend on n and m. So this is our model. We want to calculate Born-Oppenheimer potential, and we want to calculate the ion-mediated atom-atom interaction, and also the entanglement between the two distant atoms. So next we move on to results and discussions. So we have calculated 4 Born-Oppenheimer potentials. So these are atomic potential, atom-atom potential. So here the scale factor is the atomic oscillators, this length scale, AL, which is in our case, we are considering a calcium ion and rubidium atoms. So this is about 0.3 micron, the atomic atomic trap scale, which is actually the width of the ground state of the atom, motional state of the atom. And we are plotting these 4 Born-Oppenheimer potential as a function of the distance between the two atoms. So Z0 is the distance of a single atom, the center of the optical tweezer from the center of the ion trap. So we are considering a coordinate system where we are taking the origin of the coordinate system at the ion trap center. And the Z0 is the plus minus Z0 is at the centers of the two atom traps. And so they are symmetrically placed on the two sides of the ion. And you can see, so this is 1 kilohertz order, these are. So you can see that these are minus 20 to minus 20 kilohertz, these are. And at long separation, so this is, if it is 0.3 micron, so 100 means it is 30 micron or so. And so this is significant. And so in terms of this oscillator length scale, atomic oscillator length scale, this could be 100, 140. So then we have still significant this interaction between the two atoms. So here we are considering only the ion-mediated interaction. We have also taken into consideration the direct interaction, but the direct interaction at this separation is negligible. And here we are plotting the probability distribution of the two atoms as a function of Z1 and Z2. So this is unperturbed when we consider no ion, only two Rydberg atoms. Then these are, and Rydberg atoms are in the ground state. And so then we have this symmetric distribution of the probability of function, basically mod square of the wave functions, ground state wave functions. And here we are considering the distance between the two atom traps is 60 AL, so it is about 18 micron. Now, if we introduce the ion between the two atoms, then the probability distribution is modified. So here also it is the distance between the two atoms is 60 times Al. It is also 60 Al, but if you compare these two, so it is clearly visible that how ion affects the wave functions of the two atoms. And then if we increase the distance between the two ion traps from 60 to 80 Al, then this modification is not as strong as in this case. So and if we increase the distance to 110 Al, then it again reduced to the original almost unperturbed wave functions. Okay, so there is an intermediate distance where the ion-mediated interaction is quite strong, and if okay, and then what we have calculated here, ion-mediated entanglement between the two atoms. So we characterize the entanglement or non-separability of the two wave function, atomic wave function, in terms of this familiar von Neumann entropy, which we have calculated in the following way. So this two atom density matrix we have constructed, row 1, 2, and we trace over either of the atomic states, say 2, then we get reduced density matrix of the atom 1, and then we calculate. So we see that when we plot this von Neumann entropy as a function of the separation between the two atomic trap centers to Z0, so we see that this is 40, 60, 80. It is quite significant, this entanglement. And as we go far away, say 80, so 80, 100 would be 30 micron, then it reduces to, it vanishes quickly. Okay. And then we have calculated also phononic coupling between the two atoms induced by the ionic ion. So we consider the effective potentials of the two atoms and carry out this to calculate the phonons. We carry out small oscillation analysis around the equilibrium position. and find out the matrix of the generalized spring constant and diagonalize the matrix, and we get phonon modes. So we are plotting this phonon frequency square as a function of as a function of the distance of the atom trap from the ion, one of the traps. And so we have two kind of phonons. One is a stretch mode and another is center of mass mode. Stretch mode means this kind of mode, and another is the center of mass. So center of mass motion, because of the symmetry in our geometry in our model, the center of mass mode is almost negligible. This is one, it is unperturbed. And then we have here as a function of a distance, the stressed mode, one distress mode. So this, so these are scaled with atomic trapping frequency. So then you can see that as distance increases, then it reduces to the unperturbed or the harmonic oscillator frequency. So this deviation from 1 is quite significant at a intermediate or short distance. And then we have not considered Stark shape or Stark effect in our calculations because of the following reason. We could have included that, but so here what we are plotting is the energy, Stark energy of Rydberg state of ytterbium lithium system. Okay, just to for potassium and rubidium will be the same. I mean, qualitatively they will be the same. So here. This is n equal to 29 manifold. So this is the distance between, so these are electronic states, energy of the electronic Rydberg state. So this is distance between the atom and ion. I mean electronic state. So this n equal to 30 and S state, and these are n equal to 30. So these are distance of the order of 3 micron. This atom ion distance. So this is this S state is separated or distinctly isolated from the other states. So here at 1 micron, then the situation is messy because you have several, but this is the P state and this is S state, and this S state is almost like at long separation 1 by r to the power 4. So it matches with the standard long range atom ion potential, which is C4 by r to the power 4. And this is for only for S state. Okay. For other P or other, so many states are coupled. And S state is, of course, there is some shift due to but that is negligible. So it is basically the second order effect of electronic of ionic field or ionic electric field. So if we consider this, so we can reliably choose this S state as one of the states of Rydberg qubit in the case of ion atom system, even though the ionic field will affect the Rydberg state, but this S state remains. So here we are considering only the effect of the ionic field. We have not considered the effects of the Paul trap field. So Paul trap field also, this our estimate shows that this will lead to a shift of the order of few megahertz. So then we can consider some shifted and stark shifted state, S state. But if we go higher P state and choosing a particular state for as a qubit may be problematic. So that's why we have considered only the S state. Okay. So next, moving on to, so I am almost done. So as concluding remarks, so our suggestion for ion atom hybrid quantum systems, so use single atom in optical tweezer that can be transported into a Paul trap. So our model, along with photonic interface, may be used as a 3-qubit node. So this will be in the future work. One has to explore whether one can think of this system or this model as a 3-qubit quantum computer, because we have 2 atomic qubits and we have 1 ionic qubit. And perhaps then one can use this as a node for building up quantum network. Then one can do 2-qubit gate operations between the atoms, because it will be faster, the gate operation, because one has to couple the ground state. So typically, Rydberg, the neutral atoms are trapped in the ground state in the optical tweezers. But there are experimental methods, and there are, by choosing what is called magic wavelength, one can trap both ground state and the Rydberg state simultaneously in one trap. So that will give added advantage. Otherwise, one can make an admixture of the any ground, the 2-qubit ground state qubit with the Rydberg state to have strong interactions during the gate operation. So this seems to be possible with currently available technology. So with this, I conclude and thank you for your kind attention. So questions?
Yeah, thank you, Professor Deb, for this interesting talk. So time for questions. Please, if you have a question, please unmute yourself and ask.
I have one question.
Please go ahead.
Thank you for your talk. Do you plan to consider decoherence into your equations or model, and then recalculate then recalculate to see the impact on the parameter like entanglement?
Okay, that we have not looked into, but this is a good suggestion. That so we have not, in this calculation, we have not considered the atoms and ions as qubits. We have considered only a single internal state. So we have not explored that, but decoherence would be an issue, particularly due to this electric fields produced by Paul trap. So that one has to carefully analyze and see. And but in our case, there is no direct collisions between the ion atoms, because ion atoms are largely separated. But since this Rydberg states have long lifetime, and also these ionic states qubit, they have long lifetime. So I think it would be possible to do gate operations within the decoherence time. Decoherence time would be large, I think, of the order of millisecond or so. So that's why we are considering the Rydberg states. Okay.
Thank you.
Okay, any other question?
Yeah, I have a couple of questions.
Yeah,
Is
please.
Prashant, okay.
Yeah, hi. So, Bimalendu, in
Hi.
principle, you can also realize a QIQT, right?
Maybe, yes. You mean the 3 qubits entangled state,
A state with 3 levels.
3 levels.
Because if you see, Zeilinger has used this orbital angular momentum,
Okay.
to realize this kind of 3 qubit state. In principle, this would be advantage actually. You could, if you can address 3 levels together,
Okay.
and
But
also, yeah.
But theoretical understanding or formulations for information processing using QIQTs is not known. As far as I know that.
There are some like Zeilinger had a couple of papers from his group, experimental papers, and also our this guy in Agra, this person I'm forgetting his name. He has a couple of PRA papers regarding jets in QIQT. This guy, forgetting his name, in Agra, this Dialbag Institute is there. There are some couple of good papers, good quality papers. Like control jet, those kind of operations for QIQT. And
in ions and these atoms with lasers, it is easier to address qubits. Okay.
Right.
Because because other complications will come into play if you consider QIQTs.
Yeah, that is true. That is true. But in also you can sort of use EIT with your distributed thing for a memory kind of thing also, right? In principle.
Yes, memory. That's what I forgot to mention, that another motivation to look into this problem is that ions, that if you trap an ion, it lives there, stays there in the ion trap for days. Okay, and so ion has more longer lifetime, and also its coherence has long lifetime. So why not use this qubit, this gate operation between the atoms, and then transfer the outcome of the gate operations? There is some noise. Some
background noise is there. Yeah.
So then perhaps one can transfer the outcome of any gate operations to ion, and then you can use ion as a quantum memory, and atoms as logical qubits for doing operations.
Thank you.
Any other questions? Somebody's this thing is on. Can you please switch yourself off? Can you switch off your mic, please? Yeah. Any other question? Okay, I don't see any more raised hands. Okay, Professor Deb, thanks again for your nice talk.
Thank you very much.
We move on to the next talk now. In the Department of Physics at Savitri Bai